Good day everyone. Now we'll discuss about ADC interrupt programming for ARM7 processor to control the pulse width of PWM. So already I have uploaded the video regarding how to program the ADC interrupt in both software control mode and burst mode. So in this particular video we'll be discussing about how to program the ADC interrupt in burst control mode, and with the application of ADC interrupt we'll be trying to control the pulse width of the PWM. So PWM is maintained in single edge mode. So let us directly get into the program. So as we have discussed in most of the interrupt programs, initially you'll have to copy the startup.s content, and you need to make this IRQ handler be IRQ handler as inactive by putting a semicolon over here, and subsequently this set up PLL parts you will be commenting so that it doesn't vary the frequency. So these two things you will have to do, and after that this is the program. So here initially we have written this area and label, then code and read only. This is common for any ARM processor. So area represents the area that what we are going to write, and this is the label, and the code is you are specifying that this is a code, and this has to be specified, this has to be stored in the read only memory. And coming to this that is the assembler directives. EQU is the assembler directive, so wherein whatever the label that you are specifying here will be associated with the memory address. So as we have discussed in the earlier videos, all registers of the ARM7 processor does have an unique memory address. So inside the program you need to access it using the memory address only. So but inside the program it will be difficult for us to go and search through the memory address. So initially we'll be initializing the corresponding registers with the assembler directive. So coming to this AD0CR, this is the control register, analog to digital control register, and AD0DR3 is the data register of the channel 3, AD0 channel 3. As far as this particular program is concerned, I am going to dump it in the hardware. So the hardware is the NGX board. In the NGX board they have connected this channel 3 of AD0 towards a potentiometer. So that's the reason I have chosen this channel 3. So we can choose whichever channel that we want. So depending upon that we need to make hardware connections. As in this particular NGX board they have given importance to this channel 3, so I have used that one. And AD0 GDR is global data register, and AD0 INTEN is interrupt enable register, and AD0 status, the status register which specifies the analog to digital converters interrupt. Then so VIC interrupt enable, VIC interrupt select, and VIC vector control 0, vector control address. These things are for basically enabling the interrupt. So ADC interrupt we need to enable. So for that we'll be using this VIC interrupt enable, and VIC interrupt select will be selecting whether it is FIQ or IRQ. As in the previous cases I will be using only the IRQ mode. Then VIC control 0 will be having to enable the slot over there, and VIC vector address 0 which specifies the IRQ handler's position. As far as the memory address is concerned, it will be specified in this particular address, and VIC vector address will be clearing the vector address whatever the recently the interrupt that has happened in the interrupt service routine with this one. Then PWM MR1 the match register 1, and PWM latch enabled register, PINZL 0 for specifying the PWM, then PWM PCR, then PWM prescaler register, PWM MR0, PWM match control register, and PWM timer control register. So these things you can see that is the repetition of what we have done in the PWM program as such. So what I'll be doing here is I'll be mixing up the two programs, ADC program, and along with that ADC program I'll be activating the ADC interrupt, and whenever the ADC interrupt is happening, it will go and correspondingly read the content of the digital output value, and according to that it will change the pulse width. That is the algorithm of the program. So here the first one is VIC interrupt enable. So we need to check the interrupt enable register. So let us get into the interrupt enable register. So here this is the interrupt enable register, in which you can see the ADC interrupt is available over here. The 18th bit AD0 is available in the 18th bit, and AD1 is available in 21st bit. So I am going to use AD0, that is analog to digital converter 0. So I am choosing this 18th bit. So you can see that it starts from 1 2 4 8 1 2 4 8 1 2 4 8 1 2 4 8. So totally 4 zeros. Then this one is 1 2 4. So I'll have to activate this 4 and 4 zeros. So you can see that 4 and 4 zeros to activate the analog to digital converter interrupt. Then VIC interrupt select, basically I'll put 0 so that it goes into the IRQ mode. Then VIC vector control 0. So coming to this VIC vector control 0, yeah, this is the VIC vector control register. So I'm going to use the 0. So the fifth is for IRQ slot enable. So this will be enabled, and in addition to this I need to activate the slot number 18. So when I activate the slot number 18, my output, my value that I am supposed to put is 32. So fifth bit will be on, and correspondingly the fourth, the remaining bits, fourth, third, second, first and 0 will be representing the number that is representing that particular slot. So that is represented by 32. So this 32 is for activating the analog to digital converter interrupt. Then VIC vector address 0, I am mentioning it as IRQ handler. So IRQ handler I will be writing it separately. So wherein I will be writing the program for changing the content of your pulse width of the PWM. So in the case of this Pincel 1, I will be activating the analog to digital converter channel. So coming to this Pincel 1, let us check the Pincel 1. Okay, so here you can see the Pincel 1 in port P0.30, the AD 0.3 is connected. So again, this, as I have already mentioned, in the NGX board, the AD 0.3 is being connected with the potentiometer. So I am activating this AD 0.3, and that is connected to P0.30. So 29th and 28th bit I need to make it as 01. So obviously 8421, so it becomes like 1. 1, the remaining values or 0, that is like 1 and 7 zeros. So you can see 1 and 7 zeros for activating the analog to digital converter 0.3 at P0 port 0.30. And coming to this AD0 interrupt enable register. So analog to digital converter interrupt enable register. So this is the interrupt enable register. So what I am going to do is, whenever I am putting a value in the potentiometer, so that will be converted into its equivalent digital value, the analog value. Whatever I am specifying in port 0.30, that is going to be an analog value. Whatever the analog value that I am fixing over there, will be converted to its equivalent digital. After it has after the conversion has been done, interrupt has to happen. So for that reason I am making this ADINT-EN0 to get active. Yeah, if it is I'm connecting the channel towards the channel 0, I'll be activating this particular bit. Since I am doing it with the third channel, then I'll be activating this bit. So to activate this bit I need to make it this one on. So when this one is on, it is like 8421, so 8 is active. So that's the reason here I have made it as 0x08 for activating the analog to digital analog to digital interrupt that will be generated when your AD 0.3 channel is giving out the output after completing the conversion. Then coming to this AD0CR, that is the control register, analog to digital converter control register. Yeah, this is the control register. 0 to 7th bit is for selecting the channel. So as far as this particular bit is concerned, I mean this particular program is concerned, I said that we are going to do with channel 3. So since we are doing it with channel 3, the 8 will be representing for the bit 3. So as far as this particular register is concerned, your selection is made depending upon the bits, 0 to 7 bits. So each and every bit is associated with its equivalent channels. So if you want to make the channel 3 active, I need to make the third bit active. So to make the third bit active, I'll put 8. So that's the reason I have made 8 over here. And next is the 1. So the 1 is for setting the clock per division. So this 1 is for setting the clock per division. So clock per division, what I am doing is I am giving the basic value. I am not making much of its changes. So I will be putting it as 1, and the 1 is for setting the burst mode. So since I am using the burst mode, so I will be making this one high so that the burst mode is activated. Burst mode is activated for this analog to digital converter channel 3. Then this 2 is to make AD converter operational from power down mode. So this 2 is concerned with this 21st bit. So the AD converter is operational from power down mode. So that is the reason we are giving it as 002100108. Then pin cell 0 is used for activating the PWM in single edged mode. So let us check the pin cell 0. Okay, so here the PWM1, to activate that I need to give a value of 2 towards the pin cell 0. So when you give 2, your port pin P0.0 is connected to PWM output, and PWM PR, I have a prescaler register, I am making it as 2 so that my output will have a prescaler of 1 microsecond. So prescaler I have reduced it to 1. So you can always design the particular prescaler register with this particular logic. That is like you know that your oscillator frequency is 12 megahertz, and when it is if you want to find out the clock frequency that is being fed towards your timer, you need to slash it by 4, so it becomes like 3 megahertz, and your design is like PR plus 1 divided by the F clock. So PR plus 1 is PR when I make it as 2, 2 plus 1 that is 3, 3 divided by 3 megahertz, that I'll be getting a value of 1 microsecond. So that's the reason I'm making it as 2 for the prescaler register. So as far as this particular program is concerned, you need to know one thing: the analog to digital converter has a 10-bit it's a 10-bit analog to digital converter. So wherein the maximum output that I can get from the analog to digital converter will be 3FF, and 3FF is going to be the maximum. So what I'm going to do is I'll be making the PWM MR0 as 400, and the PWM MR1 value, initially I am putting it as 6, but whenever the interrupt is happening, what will happen is the value will be changing according to the analog value that I am feeding in. So the maximum value that I can feed in will be 3FF. So the value of PWM MR0 and MR1 can't be equal. So if it is equal, you will get a straight line. So that's the reason I am making it as 400, while 3FF will be the maximum value that your pulse width can have. So 400, in the sense, it will have a 400 converted to its equivalent decimal, it will give like 1024 in the sense closer to 1.024 millisecond. So since it is PWM PR is done for 1 microsecond, so here it is 400. So but this is hexadecimal, so you'll have to convert this 400 to its equivalent decimal. So when you convert that one, it will be giving a value of 1024. So that also I can show you. 400 decimal 1024. So 1024 into 1 microsecond. So obviously it is 1024 microsecond. So it is like 1.024 millisecond you can take. 1.024 millisecond is going to be your PWM MR0. That is going to be the rate, while PWM MR1 is going to be the pulse width. Here I am giving it as 6 microsecond. So subsequently, when the program is running, when you change the values of your the analog to digital converter, subsequently the pulse width will change. Then coming to this PWM match control register. Yeah, this is the PWM match control register. So as far as this is concerned, I need to make my PWM MR0 to go reset. So that is happening in this first bit. So that's the reason 2 has been given. PWM MCR is moved with the value of 2, so that my MR0 gets reset. When the MR0 value is has been reached in PWM PWM PC will be the counter, while PWM PR will have the value 2. So whenever PWM PC reaches the content of PWM PR, your timer counter will be incremented by 1, and that will be checked with your PWM MR0. And when that checking has been done, and when the value both matches each other, then the reset will happen. So this already we have seen in the PWM program again. So the same thing has been repeated over here. So coming to this PWM LER, latch enable register 3, we are giving. So this is the PWM latch enable register. So I need to enable the PWM match 1 latch and match 0 latch. So that's the reason I am giving 3. Then PWM PCR. Yeah. Here this is PWM PCR. So in which we need to select the PWM. As far as this particular program is concerned, we are going to do with single agent mode, so you are not going to activate any of these things, while PWM enable 1 will be activating. So that's the reason you are giving 200, because like here it goes on like 8421 and 8421 and 8421, so it is like 200 for activating the PWM enable 1. It is a PWM control register. And PWM TCR, coming to the PWM TCR, that is for resetting and starting the PWM timer. Yeah, timer control register. So you need to give first this counter reset. So if you put 2, it will get reset, and then when you are enabling, you will have to enable this one, the PWM enable and counter enable, so you will be giving 9. So that's the reason 9 and 2 has been specified. So this is the main program. And coming to the interrupt service routine, so what I am going to do is, as I have already specified, I am going to generate an interrupt. I am going to make the program in such a way that it generates an interrupt when when your unlock value that has been fed is converted to its equivalent digital. So when the digital conversion is over, it will generate an interrupt, and when it generates an interrupt, it comes towards this interrupt service routine. And in this interrupt service routine, I am going to extract the content of the digital value, and that value I will be putting it as such inside the PWM MR1. So as I have already mentioned, so I am not going to do any processing with the data. So whatever the data that I am getting, I am putting it as such inside the PWM MR1. But in case if you want, you can after extracting it, you can do some checking. So you can put some benchmarking. So if the value is say like 200, your output should be something, and 250, your output should be something else. So we can do it in that way. But as far as this program is concerned, to make it simpler, what I have done is I am extracting the value of the digital output, and I am putting the same raw data into the PWM MR1. So your input value that is being fed through the potentiometer, if the value is maximum, your pulse width will be maximum. If the value is minimum, the pulse width will be minimum. So that's the basic algorithm. So SUB LR, #4, this is for maintaining the offset. Then MOV R6, LR, so I am storing the content of the link register. Then LDR R3, equal to AD0 DR3. Since I am using the channel 3, I am putting it with AD0 DR3. So I am reading the content of AD0 DR3 into the R4. Then I am putting a value of 0x0000FFC0. So in this case, you need to understand one thing. So this is the part where my data will be there inside the AD0 DR3. So for that, once we'll go for this structure of the data register. Yeah, so this is the structure of the data register. You can see 0th to 5th bit it is reserved, while 6th to 15th is the result. So 6th to 15th, you can see it starts from you can see like here the 5th and 4th bit has been gone, and 3rd, 2nd and 1st and 0th bit also has been gone. So it starts from 6. 6 means its value, equivalent value will be 4, and subsequently the next value will be 8. 6 and 7th bit will be 8. So that gives you a value of C, and correspondingly after that from 8 to 15, so it's a total 8 bit that will have FF. So that's the reason you are giving it with FF, C and 0, and the remaining bits we are not concerned with. So the remaining bit over here, so overrun and done, so we are not going to check the done bit also, because we are making the analog to digital converter to generate an interrupt when the conversion is over. So as far as this particular done bit is concerned, we will be checking it whenever the conversion is over. So after conversion is over, first we'll be checking whether the done bit has gone high or not. So as far as this program is concerned, we need it's not necessary to check the done bit, because we are making the done bit to generate the interrupt. Then so what we are doing is we are putting it over here, and we are doing AND operation with the R4. The R4 and R1 is ANDed, so that only this particular bits will be extracted. So the remaining things will become 0, and the result is stored inside the R7. So then after it has been stored, so we need to make it as a meaningful value. So if it is available in these bits, it won't give a proper meaning. So that's the reason I am shifting it. This is logical shift right 6 times. 6 times the content of R7, and I am putting the value into the R8. So in case, as far as this simulation is concerned, if you want to check what is the value that has been obtained from the interrupt, we can obtain from your analog to digital converter. You can use this memory address. I am using this memory address, and I am putting it so that I can check what is the value that has been generated. If you want, we can cross check with the pulse width. It's not mandatory as far as the hardware is concerned to do this one, because in the hardware, if you want, you will have to write a separate subroutine for displaying the content. So this is for simulation purpose I have done this one. So this part is this LDR and STR part. If it is going to be done in the hardware, we can remove this part. Then LDR R0 comma equal to PWM MR1. So I am moving the content as I have already specified, whatever the output that digital output that I have got into the PWM MR1 using this instruction. Then I am putting the VIC vector address into the R2, and I am clearing it. Then MSR CPSR underscore C comma hash mode user. So I am changing the mode of my processor from IRQ mode to user mode using this one. So after changing that one, what happens is my the latch enabled register is also getting cleared. So after doing this, again I am enabling the latch enabled register using this 3. Then I am popping the content back from the R6 into LR and branch with exchange the LR. So this is the program, and in this case also you can see that the program comes and stays over here once initialization has been done. So your program is staying over here, it doesn't change, and only the value of your PWM MR1 does change. So now let us run the program, translate, build and rebuild. So in the logic analyzer, I will be using the port 0.0, and here AD 0.3 is used, and in case if you want to check the content that has been done, you can use this memory window also. So I will just put 1 volt, and Vref has been kept as 3.3. So if I am giving 3.3, I will be getting 3 FF as the maximum value. So now the program is running. You can see the rate. Let us check the rate. Rate is almost equivalent to 1.024, as I have already mentioned, millisecond. So that rate is obtained. So here it is 136 hexadecimal. 136 hexadecimal has to be converted to its equivalent analog. So has to be converted to its equivalent digital. Hexadecimal So 310. So almost closer values we are getting 310 or 311, right? So now again I am running, so let us change the value and check. I have changed and you can see the changing pulse width. So if I give again 3, and you can see this also has changed to 260, I am now giving 3. So maximum pulse width has happened, and this also has changed. So we have successfully integrated the analog to digital converter with the pulse PWM, and we have changed the PWM pulse width of the PWM using the analog to digital converter interrupt. So when we are dumping it into the board, so we need to check from where we are supposed to get the output. So you can see from here, P0.0, that is PWM1, from where we are will be obtaining the output. And as far as this number is concerned, P0 underscore A0, we need to check P0 underscore A0. So you can see that is the third pin. Third and second across will be obtaining the output, and we need to give an input, that is the analog input. So you can see ADC, as I've already mentioned, P0.30 is connected to this ADC. So ADC is connected over here with a potentiometer. Yeah, here it is. So this is the potentiometer that I am talking about. So near to the J10 connection, there is a potentiometer like a screwdriver, screw like a thing. So when you vary the when you rotate the screw, so your resistance will vary accordingly. The voltage that is being fed into it also will vary. So this is the input and output. So this will have to take care while we are doing with the hardware connection. Okay, as far as this hardware is concerned, we need to make a small change. In the simulation, we have made this AD0CR with 00210 So the clock per division, we have made it as 1. So the frequency that it is entering inside your analog to digital converter will be the maximum frequency. But as far as the hardware board is concerned, if we give it as 1, it's not functioning. So what I'll do is I'll be giving the maximum value, so the frequency is reduced so much so that the analog to digital converter is capable of accepting the analog value, and it converts the analog value into its equivalent digital value without any problem. So for that reason, we need to do this change of F08. And as far as this pin cell 1 is concerned, it is like 0x100000. I am using it to activate the AD 0.3 at port pin P0.30. So this is for pin cell 1, while pin cell 0 will be for PWM output, single edged PWM output. So this is the one that we'll have to keep it in mind while we are doing the hardware. Start. Okay, so now as we have done in the previous programs, we'll be clicking these options for target and click output, and you'll have to set this click this create hex file, so that your hex file will be created with the name pwmin.hex. so you can change the name if you want, and the folder in which it is going and saving is this one. You can navigate by pressing this select folder for objects. So it is in experiment 12 in objects. So after clicking this, you are supposed to do translate, build and rebuild. So now the hex file has been created, and next we need to understand from where we need to take the output. So in this program, so we are going to feed in the input voltage through this ADC, ADC 0.3. AD 0.3 that is connected to P 0.30. So that is internally connected. So as far as this part is concerned, we are not going to connect anything into it. So as far as the output is concerned, we are connecting PWM1. So that is P 0.0, and P0 underscore A0 is the pin that we have to check. So that is available in J2 P0 underscore A0. So between P0 underscore A0 and the second pin, we will be getting the output. So now let me dump the code. So before dumping the code, as we have done in the previous videos, we will select this advanced options, hardware config, use DTR and RTS to control and keep RTS asserted while COM port open, and T1 and T2 should be 100 and 200 millisecond respectively, and your baud rate should be 9600, COM on port, and oscillator frequency should be 12.00, and erase all flash and verify after programming you need to do. We'll browse it. So as I've already mentioned, we'll have to get into this experiment 12, and in objects pwmin.hex we'll have to click open, then start. So now the code is getting dumped. So the code has been dumped successfully. So I'll remove the RS-232 now, and I'll connect the probe to the second and third pin. So this is the third pin, the black one, and the gray one is the second pin. So towards the black one I am connecting the positive, and the gray one I am connecting the negative. So now you can see the waveform that has been obtained. So this waveform you can go for changing it by varying this particular knob. This is connected to P, that is AD 0.3. That is the third channel of AD0 is being connected to this particular potentiometer. So when I vary this potentiometer, so each and every time when the analog to digital conversion happens, interrupt is generated, and because of the interrupt it goes into the interrupt service routine. The value whatever that has been obtained from the analog to digital converter is put into the PWM MR1. So the PWM MR1's value will depend upon the voltage that is being fed from this AD converter. Now I am changing this by using this tester. So you can see the value of the pulse width is getting changed when I rotate this. So now I am increasing the voltage that has been fed to the AD 0.3. So you can see that it is going to almost maximum. Now I am moving on the other side. So gradually it is decreasing. So I am using the ADC analog to digital converter to control the pulse width of PWM1. So ADC is connected with PWM1. So now I can use the same output for controlling the chopper circuit. So now as we have done earlier, the same chopper circuit we are going to do. So for the chopper circuit, we'll take the output from this is the second pin. Second pin I am connecting to this is a ground. Actually second pin is ground, that I am connecting to the third pin of the optocoupler, and third pin of the LPC2148J2 I am connecting it to the second pin of the optocoupler. So now input has been given. Now for output of the optocoupler, to get the output, first we need to give the VCC. VCC I am feeding into the plus to the 8th pin and minus to the 5th pin. So this is the B source. B source I will have to keep it at least with the value of of 12 volt. Then only since I am using TLP 350, my output VCC should be given at least 12 volt. So I am giving 12 volt and now I am checking the output from the optocoupler. So pass one. And start. Now I have connected the TLP 250 with a voltage of 12 voltage, and you can see the output. So again in this case also I am changing the ADC. So you can see the output waveform getting changed. So this is going to be the triggering pulse that I am going to feed in the chopper circuit. Okay, now let us design the chopper circuit from from the 6th pin I will be connecting towards the gate.
Waiting outside.
I am connecting the gate, and from the 5th pin I will be connecting it to the source, and from the source I am connecting a load resistance. So as far as this positive supply, I will be giving it to the drain. So here in this MOSFET it is gate, drain and source. So from the positive I am connecting it to the drain, and from the source I have connected already the resistance. The negative is connected to the other end of the load resistance. Now I will have to keep the voltage and keeping some voltage towards the chopper circuit, and I am going to check the voltage across the load resistance. So now I am getting the voltage over here, the waveform over here. So now I am going to change the output of the chopper circuit using this ADC. ADC is 1. So you can see the output voltage is getting changed whenever I change the ADC input. So I can replace this load resistance with a motor. So when I am having the larger pulse width, my motor will be rotating faster, and in case if it is going to give a lesser pulse width, the motor will be rotating in a slower speed. So this is the explanation for how to connect ADC with PWM program. Thank you. Already we have done the circuitry for with load resistance. Now what we are going to do is we are going to connect motor with this one. So now you can see the waveform over here, and the motor is being connected in the place of the load resistance. I have connected the load resistance also along with it. If you want, I can remove this one also. So now I have removed the load resistance, and you can see this is the on time and this is the off time.
So in case if I increase the on time, the speed of the motor will increase. So now I'll increase it by varying the ADC port. So now I am increasing. You can see the waveforms on time increases, and you can see the speed of the motor also is increasing. So I have kept at the maximum. Now again I am reducing. So you can see that the speed of the motor is reducing. Almost it is going. I mean, it is like rotating like with minimum speed. So if I reduce it further, it will stop. So now it has stopped. So now again I will increase the pulse width. So now the speed has increased. So you can see the maximum speed is going on with the DC motor. So this is the procedure for controlling the DC motor using your ARM processor with the MOSFET chopper circuit. Thank you.
Thank you.